So now let's transition from the world of a structural connection meant to be there and be there all the time to connections supposed to be come apart, go together, come apart, go together. Same type of analysis in terms of thinking of the joint as a series of springs. The joint has to accomplish have some stiffness, some strength. It's just that you want it to be able to come apart now and then. Many different types of joints that can do that, from what are called pin joints, these flexural kinematic couplings we'll get into in a bit, elastically averaged or Lego type joints, you know, pins and sockets, more kinematic coupling types. How do you pick from all the possibilities? This chart here is supposed to indicate where the realms of goodness in terms of repeatability these joints can get you. A normal pin joint where you just have two surfaces that you want to hold together and you have a couple of pins in them is only good to a few millionths of a meter, 5 to 10. You say, wow, that's a lot. Well, if you're doing a high precision piece of optical equipment, that's not going to be good enough. So we'll go through these different joints, but ultimately the highest precision will come from either joints, and you see it gets kind of gray area here, it depends upon how well you put things together, where you either have a very, very high degree of elastic averaging, for example, many, many, many pins on Legos engaging, or an exact kinematic joint, one without any friction, where you know exactly where the 6 contact points are. And you get that, quote, no friction, for example, using air bearings. But let's dive into the most important thing to consider when designing a joint is if you have discrete points touching and the joint is heavily loaded, there's a very good chance you'll experience what's called Hertz contact. Hertz contact, named for Heinrich Hertz, very brilliant mathematician, the same guy who invented frequency. Well, rather doing frequency analysis, and hence the unit Hertz, or cycles per second. The lore has it that a friend of his who was a railroad person said, Heinrich, I've got this locomotive and I push on it and push on it harder and harder by loading it with weight, so it'll haul a bigger train, and I break the train tracks. In other words, I've got a wheel, and as the wheel is rolling, you see the way it's deforming the tracks, my arm? You can see that deformation field on my arm. That's what's happening even with steel on steel. And that deformation field leads to stiffness being finite. In a machine, that can be very bad if you're, for example, a machine tool, you're relying on it to be really, really high stiffness machine, even under loads. So this dude is the one who figured out the mathematics behind what happens. There's a spreadsheet, of course, to help you predict what happens with stiffness in joints. And in particular, it goes through what is the stress at the joint. A little experiment you can do in the privacy of your own study area is to help you visualize Hertz contact stresses. So take your writing instrument, pen for example, and push on the side of your head until it, ow, hurts. Ow. Turn the writing instrument to where you've got at least one side is flat, the other side can still be curved, and now push. You can take a lot more load before you hurt yourself. So how the radii of curvature of the contour surfaces engage to distribute the load is what Professor Hertz figured out. Infinitely valuable in designing joints. Because of the high contact stresses, the potential for failure at the joint can be very high. And the type of failure mode you get, well, for example, a very nice book by ASME, it's called The Failure Atlas for Hertz Contact Machine Elements. Vast quantities of very interesting failure modes have been found over the years based on different materials, how they were loaded, and whether or not they fail by a deformation right at the surface or with repeated motion back and forth. They actually have high shear stresses below the surface that cause the parts to delaminate and peel. The key thing about the Hertz contact analysis is its nonlinearity shows that the stress goes like, you can push harder and harder and harder and the stress will not rise so fast. And the deflection goes like the force to the 2/3 power. So the stress goes like the force to the 1/3 power. The deflection goes like the force to the 2/3 power. In line contact, similar relationships for the nonlinear stress and deflection as a function of force. In line contact, very important is, if you think about two cylinders, if they're crossed this way, that would hurt. Bang. But two cylinders crossed this way, not so much stress. The angle between the two will tell you, are you having point contact or the degree of line contact you have until all the way to full line contact, for example. When you're looking at line contact, also remember very carefully, can I ever really have line contact? And the issue to be faced with is, if I have what I believe is a roller on a body, and the roller is loaded, say, by another plate on top, how uniform is the loading across that roller? If the loading is applied at all such that the roller is tilted, let me draw in cross-section here. The roller is on one plate, and there's another plate above it, and the loads are eccentric to the center of the roller. Will I start getting edge loading of the roller? To address this, many rollers, by the way, are never really rollers. They always, well, many will have a slight barrel shape to them. To avoid edge loading the roller. So we can do the Hertz contact analysis, and in designing the joint, think of a kinematic coupling. Go back to topic 3 in terms of exact constraint design. And for this type of coupling, I can take it apart, put it back together, and the functional requirement is to define 6 degrees of freedom. 3 translation, 1 rotation, or yaw, roll, and pitch. 6 degrees of freedom, 6 contact points. There's 2 contact points per ball between the V grooves. Now, if you push too hard, these contact points will damage. If you don't have the grooves oriented properly, let's do this little experiment where we rotate them. And remember from topic 4, the idea of instant centers. I put this coupling together, and it looks perfect, wonderful. But there is something really funny going on here with the stiffness of the coupling. Why is that? And that is because the instant centers meet at a point in the center, which is why it's rotating about the center of the coupling. Let's try to visualize this in 2 dimensions. What if I want to locate a part, flat part on a flat plane? I want to have the z direction is just defined by one flat sitting against the flat. But what I'm going to try to do is get x, y, and rotation. Z, pitch, and roll are just going to be defined by the 2 flat planes together. Where and how can I make things kinematically? And look here at this little wooden bench level experiment I have, where we can play what if in terms of the location of 3 contact points, because we have 3 degrees of freedom we're trying to define. So let's look at this little demo I got here. I use this thing as a spare paper holder, like for recycled paper. This part I've put on it, it's touching 2 points but not to the 3rd. If I shake it, it comes to a minimum energy position against the 3 pins. Is that the best way to do it, though? Because now in this position, if I push here, it goes out of whack. It finds 3 other points, and then it's unstable. Is this lower pin in the best position? Should this pin be over here? Well, you know what? Let's do a little experiment right here in real time. Let's make a virtual version of that pin and put it up here just with this binder clip. So now I push and it goes away. If I push from the other direction, it is stable. So where to put the pin, the 3 pins, depends upon the direction of load. Should I, for example, have it down here? Let me put a little spacer for this pin. Such that I'm now contacting it at 3 lower points instead of this upper point. I'm going to take away the upper point. It's very stable in this direction, in this direction. You see, wow, that's a lot more stable than I had before. But it's not stable when I push at the top. So kinematic alignment, it can be a great tool, but like any tool, it has its limitations and it has its niche where it works best. So that's the main thought process here, is not only know the tool philosophically, build and test and feel, and then also understand the mathematics so you have a model for your coupling, apply the loads you expected to see, and determine whether or not it's going to be stable and stiff enough or not. The moral of the story is that you can couple things in 2D, very, very low cost, with these kinematic arrangements of pins. In 3 dimensions, as we showed here earlier, you can couple 3 balls to 3 grooves. This was a type of kinematic coupling that James Clerk Maxwell, dude of light, favored. And then Kelvin, pretty hot dude, favored ball in a tetrahedron, ball in a V groove, and ball in a flat. And also notice very carefully here that this groove points toward the tetrahedron. I've seen some people do these couplings where the groove is not toward the tetrahedron. The key in these things is to make sure that the instant centers are such to maximize the stability of the design. I have here a version of both of these. So here you see we have 3 grooves, 3 balls, and gauges the coupling. Three balls, ball flat groove, and what you'll notice here, this was a present was given to me, that the groove is not facing the tetrahedron. It's still going to be stable, so it's not wrong, but it's not as stable as it could be. It should be stable, period, but it won't be as stiff as it ideally could be. Okay? All of these rely on using Hertz contact theory to predict the stress between the ball shape and then the groove of the tetrahedron shape. All of these can be manufactured by machining as it was shown here. you can make a V if you don't have to have high load capacity just by taking a rectangular slot and putting in a couple of rollers such that the ball then rests on the rollers. You can take a half sphere on what is called a Gothic arch. The Gothic arch being, if this is the center of the sphere, the center of this arch is located over here, and the center of this arch is located over there. The purpose then is you're making the groove become more and more conformal to the shape of the ball, and you can handle higher and higher loads. All predicted by the Hertz contact theory, which is very, very accurate, by the way. How would I use this thing? Well, here's an earlier patent, 4,574,625 by Federal Products, where this was a probe for a measuring machine. And if you've ever used a measuring machine, you'll find sometimes that when people aren't being as careful as they should be, they drive the probe into the board and break it, or into the part. So what Federal Products did is they put a kinematic coupling where they used magnets to preload the two halves of the coupling together. And if you push too hard, the magnets just bloop, let go, and you could pick up the probe and snap it right back on. Very, very useful. So very high rigidity, very high repeatability coupling, instantly replaceable. So how do you design these things quickly? Well, in the simplest case, laying it out before you hit to the spreadsheet, you have to establish the limits of where you want to be located. So for example, if I had something like the head of a laser, and I want to locate this laser in my experiment, I want to take it off for doing some sort of maintenance or out of the way for reconfiguring the experiment, but I want to put it back the exact same place, and I have a couple of round feet at the front, and I would have in the back another round ball. So if I look at the top view of this thing, I have a ball here, here, and here. And generally, you start by putting your points, contact points, as far out as possible. Next, you draw a triangle that connects the points. And the triangle doesn't have to be an equilateral triangle. It can be any shaped triangle. Equilateral, if that's what your body encompasses, great. But don't force an equilateral triangle, for example, on the laser head just because you think all three legs have to be the same. It's more important that the legs or the points of contact are spread out as wide as possible to give yourself a good stance. Now, where do I put the grooves? We saw earlier that when I went from the grooves all facing toward the center to being faced like this, I lost my stability. Well, it turns out that the grooves, I had a student, Bobby, who once created this experiment for me, which is really nice, this learning tool. See, it goes together very nicely. And the grooves are aligned to the center. They're not actually aligned to the center in all cases. What they're aligned with to get the best overall stiffness is through the angle bisectors. So for a equilateral triangle, yes, they pass, the axis of the grooves passes through the center of the triangle, the centroid. But here, I'm going to pass off from the centroid. Remember, the centroid of a triangle is when the lines connect the midpoints of the opposite sides. And then where the three lines intersect forms the centroid. more important that you, for the kinematic coupling, align the grooves is the angle bisectors. Now, of course, there's a spreadsheet that goes with this where you could go and play what if. What if I don't align things exactly along the angle bisectors? How would it affect the stiffness of the coupling? So go ahead and experiment with that if you'd like to. Spreadsheet, of course, calculates, given the size of all the components and the loads, what are the deflections and stresses. You could write one yourself, too, to do a check. The theory is all well laid out in the papers that go with the text. Some of you may not like using a spreadsheet. You want to use MATLAB, so you can play what if. How would I detect the sensitivity of my coupling if the load varies a little bit because the stiffness of the point contacts is far less than if you had two plates and elastic averaging? The kinematic couplings are a softer interface than two well ground and bolted together objects, which aren't very kinematic and you don't necessarily know where they're going to go. I mean, I can't have my cake and eat it too? Possibly. We'll come to that in a minute. Okay? But the moral of the story is it's very deterministic, easy to design. Now, we just alluded to the fact that kinematic coupling is great for aligning two surfaces, but because of the finite Hertz contact stiffness, there is some softness in this thing. If I were to push down on it hard enough, I would either break the balls or the grooves. But because things have finite stiffness, and for example, even this giant V groove, so this is from a very, very big industrial robot we did, where here's a V, and this shape looks, we call it a canoe ball. It's not actually a V, it's a surface with a half-meter radius of curvature in 2 dimensions. So it looks like a section of a very large sphere. So you think, wow, that's got to be plenty stiff compared to just a wooden ball in the V groove. Sure, this is much, much stiffer. But in a giant robot with giant loads, where you still don't want any deformation, it still is finite. Can we design the coupling such that when we push on it, for example, the V is on a flexural bearing spring such that it will then deflect and then let the two flat surfaces come into contact? How do we design in desired compliance into that ball V groove coupling or interface to give us the, when it first engages, to locate and then to displace to allow two flat surfaces which now can have very, very, very high stiffness to come into contact. So that's the essence of what a compliant mount kinematic coupling is. Must it be a ball in a groove? Can we get something that's good enough? On our way to something called a tooth coupling with many teeth and elastic averaging, this is a 3-tooth coupling. And in the ideal world, the teeth are designed such that one surface has a flat surface and the other one has a spherical surface. So you still end up with exactly 6 points of contact. Or they both have a slight spherical surface, so the two parts are exactly alike. And because the radii of contact can be very large, it still looks like a flat on a flat. So I had a student long ago, Leighton Hale, who designed this specific type of coupling. This is actually one he made himself. And the nice thing is in this instance, it's 2 exact parts that come together and have very high stiffness. Notice that the 45-degree contact angle here, if you were to use this as a joint like for transmitting torque and you applied too much torque, it would slip out. But when properly preloaded, this could transmit enough torque to shear the shafts off. Can you make this an injection molded plastic just with flat tooth to flat tooth and still have it work good enough? I bet you with the teeth being of finite stiffness and length, you can actually have them just be flat on flat and they'll come together. Apply a little bit of load, the teeth will deform, and it'll act like an elastically averaged part, and you can make a very, very low-cost plastic coupling, very, very high load capacity and stiffness, all with 3 teeth. What if I want even more teeth for more load? This is a part of a coupling that normally you would have teeth all the way around. This is rapid prototype, which is why I have this 2-part one. And you can see when teeth come together, if you're within the range of motion of the angular displacement of a tooth, when you push on it, it will force it to rotate in alignment. And once in alignment, if you clamp it hard enough, the teeth will deform, and now it'll look like a solid joint. So tooth couplings can work very effectively. There's many different types of tooth couplings out there. Again, get a design catalog from one of the online hardware places, McMaster, for example, being one. Small parts. There's a number of companies that will sell small drivetrain components where if you look under couplings, and not the pipe couplings, but for servo systems, an amazing array. And what they all do is they seek to allow one shaft, one part to transmit forces to the other with a certain accuracy between the two. In particular, also allowing for a certain misalignment of things, either during operation or when they're fully preloaded and locked together. What else do we want a coupling to do? Well, if I structurally bring something together, that's great. Don't I often also now, if I wanted to have a robot arm or some machine part, a modular machine changes its end effector, how could I also pass fluids and electrical services from the machine to the hand, the part that I've just coupled? Often you'll find that in machines, the function is defined for structural coupling, and then services coupling. This may be, for example, a ball groove. Down here, this could be a pin connector. Just like in the simplest form of a pin connector, plugging the plug into the wall. This means I have to have some design element. And here's another part, right? The connector. This is going to have to locate one part with respect to another, allow continued travel inward till the connector is made, the electrical connector. Well, that works, and that's pretty standard. If the number of connections you need is more finite, including for fluid connectors, you can consider the following, that the Hertz contact zone is not actually a point. If I have a V and then here is the ball, in the ideal world it's a point, but it's not. Remember, there's going to be some deformation of the Hertz contact zone. And if I had a hole going through the center of it, of each element, I could then pass the fluid. It would seal just by virtue of that very, very high stress in a very small space, causing high elastic deformation of the bodies. Or if I was having electrical contacts, they could also be compressed and have very good low electrical resistance between the two elements. So you can combine functions with these couplings. Very powerful tool, if they're limited in terms of the number. And this patent is long expired, so anyone can use it. Let's look at a practical example. Semiconductor wafers. Semiconductor wafers are carried around in cassettes within the factory. And what you see here is a tool, and this big black cube, come about the size of a milk crate, holds semiconductor wafers, silicon wafers. And if my friend could pass me my wafer cassette right behind him, yep. Just happened to have one lying around the office. Can you believe it? Well, this is for 200 millimeter wafers. I did a lot of work with MITx over the years. And this shape on the bottom here is called the H-bar. And it was an evolved design through many years, starting with smaller wafer carriers, trying to make everyone happy, which it did for a while. And this H-bar would mate with another H in the tool. But you see, because it was these lines, and all these lines have all these tolerances, there was always some rattle that happened. And in the end, the H would never properly exactly line up. The result is, when you put the part down on the tool and the robot would come in to get the wafer, it would sometimes bang it, which would break the wafers, which is bad. So I came on the scene for another part of design review and work with MITx on the robot end, and was very frustrated with how poorly these cassettes were located. And when the move to a 300 millimeter wafer was suggested, I did the analysis that showed there's no way that you would not be able to be breaking wafers a lot. And I took, and unfortunately the original is still at MITx, one of these cassettes, and I looked at it and I glued on 3 grooves. Or I might have put balls on here and then the grooves went on the machine. I don't recall which one. I think we put the balls on the cassette. By having a groove, a ball, and then on the back side here added a bar and another ball. Made it kinematic. And it was thus able to show analytically that because I always knew where the wafer cassette was, the robots could pick the wafers out of the cassette with very, very high accuracy. That went through very, very quickly with contacts and friends at MITx, industry working together to define, and in the end they wanted the grooves on the cassette and the balls on the tool. And the reasoning is very simple. If the grooves were on the tool looking up, dirt could get in the grooves and contaminate it, and there should never be that level of dirt in any of these tools anyway. But we're talking dirt on the micron level and smaller. But by the grooves being on the bottom, they'll stay cleaner, and the balls, any dirt that falls, and when I say dirt, remember again we're talking submicron particles, just sloughs off. Standard, all 300 millimeter wafers, and even now the new big 450 millimeter wafer cassettes, all using these couplings. Allowing a robot to come in and place with not that great accuracy the cassette, and then it will snap into place. See how that just dropped? I'm not accurately aligned, but I put it down and it comes right into position. Very, very powerful machine element tool for you to use.